Okay, why don't we get started? Welcome to yet another workshop sponsored by the Office of Research. This one's on power analysis, as you know. And so there are three of us that will be sort of tag teaming presenting. Richard Lomax, we have Susie Malk, and Robert Nichols, two graduate students in the CREM program. And so what we're going to do is go through sort of the basics, underlying power analysis, then get into the software, then get into a demo. So I'll turn it over to Susie.
So I want to start by just kind of giving you an outline of what it is we're covering today. First of all, we'll be talking about, obviously, an introduction to power and what it is. Why it's important to conduct a power analysis while you're during the planning stages of a research project. What you need to conduct a power analysis and ways that you can increase power. We'll talk about the different purposes of a priori and post hoc power, and then we'll finish up with an overview of some of the statistical software that programs that are available to conduct a power analysis, and then have a demonstration of G-Power, which is a free power analysis software that you can get online for free. So what is power? Well, before we even talk about what power is, it's helpful to review the difference between the two types of errors that you can make whenever you're making a hypothesis decision. So a type 1 error is when you reject HO when HO is really true, and a type 2 error is when you fail to reject HO when HO is really false. And I remember reading this for the first time when I took intro stats, and I think I had to read it about 10 times before I understood what it was saying and could even think about remembering what it might be. And then even then I would go back if I was reading and I'd be like, which is the type of error? So I'd have to go back. And so I'm going to avoid using language like this in favor of more plain language and visuals. So when you when you're doing a hypothesis test, you can make a type 1 error, and that would be, if you could make a type 1 error, you find a difference when a difference isn't there. So if you look at the windows on the left, and if you think those windows are different, then you are committing a type 1 error because you're detecting a difference when a difference isn't there. I like to think of it as finding it when it isn't there. On the other hand, if you don't find a difference when a difference really is there, so you look at the windows on the right and you think they're not different, then you're committing a type 2 error. So you are missing it when it is there. I also like these images that kind of help me visualize the two types of error. So in this case, the null is that you're not pregnant. And the doctor on the left is clearly making a type 1 error because he's telling the man, who is obviously not pregnant, that he is pregnant. And the woman on the right, the doctor on the right, who's examining a woman who is clearly pregnant, is making a type 2 error because she is not detecting a difference when a difference is actually there. So when you're doing a hypothesis test, there are 4 possible outcomes that can happen when you're any type of decision that you're making in a hypothesis test. And 2 of them are when the null is true, and 2 of them happen when the null is false. And so imagine that you wake up in the morning and you have to decide whether you're going to take, it's sunny, and you have to decide, okay, is it going to rain later today? Should I take my umbrella? And you're not sure if it's going to rain, so you have to make a decision. So if the null is true, and it doesn't rain, and you don't take your umbrella, that means you failed to reject the null, that you have made a correct decision. You correctly failed to reject the null. If, on the other hand, the null is true and it doesn't rain, and you take your umbrella, so you reject the null, then you have made a type 1 error, and you look silly. Because you've taken an umbrella, you're over-prepared, you didn't need your umbrella. If, on the other hand, the null is false, and it does rain, and you didn't take your, you failed to reject the null, you didn't take your umbrella, you're going to make a type 2 error, and you're going to get wet. If the null is false and it rains, but you reject the null and you take your umbrella, then you have correctly rejected the null. That's what power is. So it's when you reject the null, when the null is actually false. This decision table, I included it for your reference. This is the more textual version of that table, and it includes the probabilities of making each type of error. Whenever you conduct a hypothesis test, you have to balance the chance that you're going to make each type of error. You can't make both types of error in the same test. There's only one of the nulls is going, either the null is true or the null is going to be false. So since you don't know which is true, you have to balance the relative risks of making both types of error. And there are consequences to making both of these types of errors. So in this scenario, this is like about a year and a half ago, Hurricane Sandy was coming towards New York City, and Mayor Bloomberg had to make a decision about whether or not to order an evacuation, and to decide, he needed to decide if the hurricane was actually coming. So if he's more willing to risk making a type 1 error, then he could conclude that Hurricane Sandy is coming, order evacuation, and if the hurricane doesn't come, then he's made a type 1 error. But what's the consequence of that? Well, if you make too many warnings like that, or in this situation it's a warning, you know, if you warn people too many times that a hurricane's coming and it never comes, then they're going to stop believing you. So there is a consequence to making a type 1 error in this case. There's also a consequence to making a type 2 error. If Mayor Bloomberg concludes that the hurricane is not coming, and it does come, then the consequences are possibly that people will die. So there are consequences for making both types of error. So which is worse? Well, as a famous professor of mine once said, not once, about 1,000,000 times, it depends. Those of you that know Dr. Lomax will appreciate that, I think. Let's see. So, what is the appropriate level power to set? Many of you probably know that the convention is to set your power level of alpha at 0.05 and your power level at 0.8. So when you set the power at this, that's the balance that you're deciding that the chances you're willing to make of both types of error. But what does a power of 0.8 really mean? And where does that 0.8 come from as our choice for the convention of our typical level of power to set in the social sciences? Well, Jacob Cohn, so we have him to thank for many of the guidelines or conventions that have been adopted in statistics, and he proposed this as the convention, that alpha level at 0.05 and a power level at 0.8, because he felt that researchers in general would think that committing a type 1 error is 4 times worse than making a type 2 error. And this became known as the 580 convention. I don't know if any of you had ever heard of that, but 5, 05, and 80 convention for 0.8. And he actually didn't he actually hoped that when he wrote this, these guidelines, that people would actually treat them as guidelines and not make them the rule that we follow. They really are more like guidelines. He had hoped that people would, each time that they did a research study, that they would try to evaluate the relative risks of making each type of error and decide each time what to set alpha and power at. That has not obviously become the rule. And so generally, if you want to be published, or reviewers generally look at a power level of 0.8, and that is generally considered the accepted rule now. So what does it mean? Well, a power of 0.8 means that you are comfortable accepting a 20% chance that you will miss the effect that is really there. So why is conducting a power analysis so important, particularly during the planning stages of your research design? The most important reason why you should conduct a power analysis while you're planning your research design is because not doing so will make you waste resources. So in this, my little visual here, we have a guy chopping down a tree, and he's using that giant tree to make a tiny little toothpick. So he's wasting his resources. You waste resources if you use a much bigger tool than you need to detect the power to detect the effect that you're trying to detect. So in this case, the tool is your sample size, and the little p is the effect that you're trying to measure. You also waste resources if you have too little power. So in this case, the tool is your sample size, and if your sample size is too small to detect the difference that you're trying to detect, you have used up time and money and resources and not detected an effect, so you have no results that you can report that are significant, and your results are inconclusive because you didn't have enough power to detect the effect you were trying to detect. So probably one of the other important reasons to conduct an a priori power analysis is that it is required by many grant funders for your dissertation if you're a PhD student, or when you submit a paper to a journal. You just need to do one because it'll be required. Otherwise, you won't get the funding that you need. Conducting a power analysis during the planning stages means you've thought out all of the aspects of the study design and then statistical analysis before you've even started to collect the data. And figuring out how much power, I messed up, didn't I? Okay, did I get that one? Did I go to the next one already? Okay, so, you need to plan. And not doing so is a bad idea. So a poorly planned study rarely yields a significant, meaningful result. And I'm going to turn it over to Dr. Lomax.
I love this slide because the engineers are pointing at each other, and it's like you didn't know like 2 months ago that something bad was going to happen, and you waited until they were 2 feet away. Anyway, just to reiterate a couple of things that Susie mentioned. One is rules of thumb. I always say rules of thumb are probably not a good idea. Rules of thumb become rules. Then people forget why they were rules of thumb to begin with. And so the 580 rule, why is that a rule? Someone proposed something, it was not empirically based. The same with using alpha equals 0.05 as your level of significance. Supposedly that was developed by Fisher, who developed the analysis of variance and about a zillion other things. When asked later in life why he picked 0.05, he said, I don't really remember. It just sounded good at the time. And so no one evaluates these rules, they just become rules over time. So this section's on determinants of power, and so these are sort of the major things that influence power. Number one is your level of significance, whether it's 0.5 or 1.0 or 0.1 or what have you. As we'll see, sample size is the one that's most under the researcher's control, and so that's the one that's probably the most important. And then the effect size, there are lots of effect size measures out there, depending on what hypotheses you're testing and what statistics you're using. And so that's just sort of a short list of some of them. So for instance, Cohen's D from the same guy, Cohen, is used for looking at t-tests, R for correlations, omega and eta square for different sorts of linear models, and partial eta square. So one way that we can increase power is by increasing your alpha level. And so for instance, you might say, well, let's make our alpha level 0.10. And so that will generate a higher degree of power. The problem is that's not generally well accepted in most publication outlets, and so that would generate a different sort of problem. So we say kind of reject that notion. That's rather unfortunate that the literature is so much driven by your level of significance, but that's sort of the way it is. It would be nice if someone could make a case in an exploratory study that an alpha level of 0.10 might actually be worthwhile, because that would say it looks like there's something there. That's not for me to determine. We can increase power by increasing sample size, and so in the planning stage, this is the thing most under the researcher's control. This is the area where people probably have the largest problem. And so if someone's designing a study and they say, well, an N of 15 sounds good, five in each of 3 groups. It's probably not. But this is the point to conduct a power analysis in the planning stage. And then lastly, power can be increased by increasing the effect size. And so the idea there, Frankenstein is a rather large effect size. He sort of wreaked havoc on the entire village. But certainly it was not under the researcher's control. If we had control of the effect size, we wouldn't have to worry about anything else, basically. So again, the idea is that the larger the effect size, the easier it is to detect. And we don't need a million cases in order to detect an effect size that's really large. Now there are some other ways to increase power, and that has to do with having a stronger design. And so those are just some examples of ways of having a stronger design that would make it more likely to detect an effect if there is one. And so you could add a covariate, which is some extraneous variable that you might want to take into account. The use of better measures. This is an area that in statistics most people don't talk about. Mainly most statisticians are not in the social and behavioral sciences, and so they have no conception of psychometric properties. So they assume everything is fine, and it's not. So if you're using a measure that's not very valid and not very reliable, guess what? Bad things are going to happen. Or you might have multi-site studies where you could increase your sample size, and perhaps at each site you had a relatively small n, but across the scope of the work you might have a larger sample size in total. So in terms of doing a power analysis, the one thing we have to know is what is the effect size? So the question here is, how do we figure out what it is? And so the first thing to think about is previous research. And so if you're in an area of inquiry where there have been previous studies, you can look at the effect sizes for those studies. By and large, for lots of journals, reporting effect sizes has become mandatory in order to get published in those journals. And so you could just pop the effect size out of an existing study. Alternatively, if an effect size is not given in a study, you may be able to compute it from the information provided. So if they would give certain descriptive statistics or certain test statistics, you could compute an effect size from that if they have not. In some cases, there might not be agreement of what the effect size is across the whole host of studies that are out there. No problem, we can just sort of establish a range that the effect size is from, half a standard deviation to a full standard deviation effect. And so we can say, well, what sort of sample size would we need within that range? And so we can plan accordingly there. Or if we have no idea what the effect size might be, we probably don't want to submit that for grant review, because one of the things that Susie mentioned is the importance of sample size and effect size in a grant proposal. So having sat on proposal reviews, this is something that's always considered, because if it looks like you don't have enough power to detect an effect in your study, why should they give you $10 million to conduct that study? And the answer is they should not. And so they want to know if you know enough about statistics, if you have a large enough sample size so that their investment in your work is worthwhile. Same for a dissertation. I mean, no one wants to do a dissertation and not find anything. And so if your sample size is real small, that's much more likely. And so that would be something to attend to in the planning of a dissertation. But again, if you have no idea, you could conduct a pilot study, get some sense of what the effect size might be. And that's probably a good idea in any new area of inquiry anyway, just to get a sense of what's happening. Now here's a little table. I'm not going to say much about it, but according to code standards, there's sort of 3 levels of effect size. I think there's a laser on here somewhere. There we go. Well, anyway, I can walk. So Cohen has sort of three standards for effect size: small, medium, and large. Actually, I've seen, super size and all that. The rows correspond to different statistics or different measures of effect size. And so this is just sort of expanding on the rule of thumb sort of idea. But for instance, with R squared, which is a squared correlation, an effect size of 0.01 is thought to be small. Well, it doesn't get much smaller than that because the smallest is 0. So that means you've explained 1% of the variance. What Cullen was pretty clear on in his work is that these standards were specific to the social and behavioral sciences. And so if you were in some other discipline, that would not be seen as a small effect. That would be laughable. Now there's two types of power. Susie alluded to these a bit. And so we have a priori power. And so this is before you have any data. This is in the planning stage. And so we all give a thumbs up to this. This is the time to conduct a power analysis, really, because if you need to know what sample size you're going to need in order to conduct your work, this is the time to do it, not after the work is finished. But this is called a priori power analysis. Then we have post hoc power analysis. And so this is, you've collected the data, you've probably already analyzed the data. This is what the power is. And so that's kind of what we think about that. Here are a couple of articles. The title of the bottom one is most noteworthy. Post hoc power analysis, an idea whose time has passed. But for certain software programs out there, for instance, if you're using SPSS, typically you can get a post hoc power estimate. So I've got a couple examples of that. So here are a couple of pitfalls of doing post hoc power analysis. In other words, you've not done any a priori. You've got a study with an N of 2,600. You're looking at males versus females on the 5th grade science test. Here's a plot of the data. So we've got males and females, and so the p-value of whether there's a significant gender difference is awful, 0.658. The effect size as measured by partial eta square, 0.01. So in other words, gender explains 1% of the variability on the science test. And the observed power, the post hoc power, 0.07. Meaning the likelihood that there's anything real there is small. And so the problem with observed power here is people don't know much about power analysis, look at that and say, oh, if we just increased our sample size, we could increase power. And the answer is, yes, you could. But look, you've already got 2,600 students, and so you might need like 2.6 million to have enough power to detect an effect that's still going to be minuscule. And so the idea here, why bother? There's no effect there, and so increasing the sample size would just be a total waste of resources. On the other hand, we have a small scale study here, 15 subjects, 5 in each group. And so the 3 groups are the sugar content of whatever it is that they're consuming. So we've got 3 levels, 1, 2, and 3. And so does the amount of sugar ingested affect memory on some recalling words task? And so here the p-value of whether there's a difference between these 3 levels is 0.055, not quite significant using the 0.05 rule of thumb. Effect size is 0.38, so about 38% of the variability in memory is explained by the sugar content variable, which if we went back a few slides, that would be a pretty strong effect. Power was 0.57, so not at the acceptable level of 0.80 using that convention. And so this would be a situation where one would say, there's an effect there. We just didn't have a large enough N to detect it. Therefore, in a follow-up study, we should increase the N. So this might be something that comes out of a pilot study. And you say, well, there's something there. Give us 10 million and we'll come up with something wonderful. Now, in the old days, this is Cohen's book from 1988. If you have insomnia, this is the book for you to buy. The book is about 800 pages. About 500 pages are tables just like this. And so before we had power analysis software, you would go to one of these. You would go to Cohen's book. Each chapter is like on a different statistic. And each page is on something very specific. And so this page here is for out of the analysis of variance chapter. And it's for a certain alpha level and a certain number of groups and things like that, very specific. And so the columns are the different effect sizes, and the rows are the sample size. And the numbers are the power. And so this 95 is power is 0.95 given all those conditions. So you would just go to this table. Of course, nowadays it's all been computerized, and so unless you want to have this book on your shelf like I do, we don't. So next we come out to the modern take on this using some power software. I've got plenty of time.
Okay. Everybody hear me all right? Okay, cool. And so I'm going to talk about some different options that are out there for power analysis software. We'll kind of give a brief overview of a few of the different packages and have some screenshots so you can get an idea of what the user interface looks like. And then we'll go to some examples in G-Power. So this first table lists the most common and most popular power analysis packages. You have some programs that are specifically dedicated to power analysis. So that would be G-Power, PASS, SPSS has a sample power add-on. And as you can see from the columns on the right, G-Power is free and has much of the same capabilities as PASS, which costs about $800 per year. Yeah. Also included the three most popular statistics packages that are sort of widely used. You have SAS, Stata, and SPSS. And with SAS and Stata, you can do power analysis, but you have to do the syntax programming yourself, so that's more kind of time intensive. And SPSS only does post hoc power, which really isn't that useful for planning studies. The last program on the list is called Optimal Design, and that is another free program that's used for multi-level analysis or meta-analysis. And so if that's something that you're interested in, I recommend downloading the program and playing around with it, but we're just going to focus on G-Power today. This is the same table, and I've included links to the specialized software packages in case you're interested in that. Okay, so this first slide, I have some screenshots from PASS, and we're just going to go through this really quickly to give you an idea of what the user interface looks like. You can see with PASS, it's another point-and-click setup, and you have a lot of options and a lot of things you can customize for your analysis. It's very user-friendly. You get very detailed output. Helps you interpret your results. But keep in mind, this is $800. So, yeah. And so this is a screenshot from SPSS's sample power add-on, which is also $800. So, hopefully it's worth it. And it's another point-and-click user interface, set up very intuitively, and It gives you a lot of options for customization. Here are screenshots of the SAS syntax and Stata syntax. Give you an idea of that output. So you can get a lot more output, but it requires a lot more of the programming knowledge. And these last screenshots are from optimal design. So again, you can see even for conducting power analyses for a multi-level study, the user interface is still pretty user-friendly and gives you the point-and-click menus. And so now we'll transition to examples using G-Power. And what I'd like to do is go through the demonstrations live, but I have slides of my examples that we're doing. So when this slideshow has been uploaded to the Office of Research website, you can go back to this and, yeah, in case you forget what we're talking about. And, okay. Okay, how do I minimize that? Sorry. I'm not a Mac person, so just pull up G-Power. Yeah. Okay. All right, awesome, thank you. So if you have downloaded G-Power already, you can follow along with the examples here. The first thing you will probably notice with G-Power is that it doesn't allow you to resize the windows very easily, but if you, so this is what it looks like when you first open the program, and you can see that it cuts off the buttons at the bottom of the screen. And so if you go to Window and tell it to hide the distribution and protocol, it will make the window smaller and then easier to use. And so the first example that I'll walk through is for the two-sample t-test, and I'll go through everything step by step because a lot of the things I'm going to show you can be applied to any of the analyses that are in that you can study with G-Power. So you have your default settings where you have your test family, and so we're going to stick with t-tests for now. And you have your default statistical test, which is for correlation, and we're going to go to mean differences for two independent means. And we're going to stick with the a priori type of power analysis. Yeah. And so G-Power has 5 options for the different types of power analysis, and you can select which type of power analysis you're doing based on what parameters you want to use to estimate and what you're trying to estimate. And since the focus is on a priori power analysis and planning for study design, that's what we're going to stick with today. So this section on the left is where your input parameters are, and so this is where you specify the different conditions of the study that you're planning. So you can say if you can specify if you're going to do a one-tailed or two-tailed hypothesis test. You specify your estimated effect size, and so for the t-tests, you're specifying Cohen's d, and you'll notice if you hover over that input box, Cohen's guidelines pop up in case you forget. The next box is where you enter your alpha level, and then below that is where you enter your desired power level. And so you'll notice that the default value here for power is 0.95, but we're going to change that to 0.8 since that is the convention that everybody uses. The last box is for the allocation ratio. And this is the ratio of sample sizes for your two groups. So if for some reason, or you are planning your study and you're trying to plan for an unbalanced design where you have maybe twice as many people in your treatment group as your control group, you can play around with this setting and it will do the calculations and give you the group sizes that you want. But for this example, we'll stick with the ratio of 1, so it gives us a balanced design. Okay, and so we'll change our tails to a two-tailed test, and we'll change that to 0.8. Okay, and so when we click calculate, it gives us our output parameters based on the information that we provided. And so the really important thing to pull from this is the estimated total sample size that you need to achieve power of 0.8. So in this case, with an effect size of 0.5, we would need a sample size of at least 128 people to have sufficient power. Okay, and that's a good question. The wrongness of the null hypothesis. Yeah, it's one of the things that's given to you, but I have never encountered it in studies that I've read or any analyses that I've done, so I don't really know what to do with it. But yeah, for other types of analyses, it will ask you for that information, and I don't think any of the examples we have planned today will require the non-centrality parameter. So
do you read it as p-value then? Like a p-value, but
yeah. Okay. Yeah, so we've calculated our estimated effect size, and so now I'm going to show you my favorite feature in G-Power, which is the graphical procedures. And so when you click on the XY plot for a range of values, this pulls up the graphing window. Excuse me. And the first thing, sorry. Okay, so the first thing you want to notice is the different options you have for your parameters at the bottom of the screen. So using these two drop-down menus, you can decide what you want to have plotted on your y-axis and your x-axis. And so we'll leave this on the default settings to plot sample size against power. This section down here, the plot number is where you specify how many curves you want to plot. And we'll leave this at 1 for now, and then I'll show you how to plot multiple curves on a single graph. And again, you can select what input parameters you want to use to create the plots. So when we first open this window, it will copy over the effect size that is entered or calculated in the main window. And when I show you how to draw multiple graphs, we'll have to pay special attention to that, because G-Power will change it when it first does the recalculation. And so when we click Draw Plot, we get this really nice graph. It has all of our input parameters specified across the top, and this line represents the total required sample size to achieve a certain level of power. And so you can see here for a power of 0.8, we can go up and see that that's right around 125, 130. And so you can use this to kind of help you visualize Maybe any added benefits of sampling a few extra people. Typically when you're designing your study, you want to plan to sample a little bit more than the minimum that you need to allow for missing data or dropouts, that type of thing. Yeah, so that's pretty cool, and this can be copied into Microsoft Word or PowerPoint or whatever, whatever presentation you're constructing. And so we talked about this a little bit. When you're doing, or you're using a power analysis to plan for a range of effect sizes or to estimate a range of sample sizes, we can use this graph and plot multiple lines. So when we change our plot number to, we'll change it to 5 for this example, but you can plot up to 10 additional lines. Now here, on the Mac version, the program does not automatically redraw the graph, but if you're using a Windows computer, G-Power automatically updates the graph, and you have to remember to change the effect size back to the value that you want, because it will change it to its default value of 0.1. So for this example, we did our initial estimate for an effect size of 0.5, and so what I want to do is change our initial value so that when we plot these graphs, we are looking at the range of effect size above and below 0.5. And so I'll actually change this to 0.4, and so the first curve that it plots will have an effect size of 0.4, and then it will add 0.05 to the effect size and redraw the graph. So leaving everything else the same, we click Draw Plot, and so now you have a very nice graphical representation of what your estimated sample size is for a range of effect sizes. So if you, prior research suggests that your effect size is somewhere between 0.4 and 0.6, you can use this and say that, okay, I need at least 75 to 80 participants if we have a very, have a stronger effect size, and if our effect size ends up being a little bit lower, then we could need as many as 200 people in the study. And yeah, so I find these graphs very useful for visualizing how many people we need to try to recruit and sort of visualizing the range of effect sizes that we're using to estimate these curves. And yeah, so that's the first example. And when you're done with this, you can just close the plot window, and it'll take you back to the main screen. And so now I'll show you a sure. Yeah, so when we do this, we'll keep those parameters here. So this is the graph. If you click on the Table tab, this is just giving you what the different effect size measures and the different, let's see, that's sample size. Yeah. Okay, so this column's power, and then these are the effect sizes used.
Sample needed, that's the sample size?
Yeah, so these are the estimated sample sizes under those two conditions. Yeah, and
I just didn't know how I was going to get that 0.006 per person.
yeah, usually just round up. Yeah, yeah, I don't know. It does give you the table if you want to actually look at the numbers, but I find the graphs really important, so I don't really play around with that. But cool. Yeah, yeah. This is Cohen's book. This is the 2000s, and so yeah.
You haven't told us how to extract a D
Yeah, so the next example we're going to do, so we can do the, I can show you the determine button using the t-test, or we can move to another example and I'll show you that. So, okay, we'll go with, we'll just look at D, the determine window for D real quick. So if you don't really know what Cohen's D is for the measure that you're planning to use, you can click the determine button and enter the descriptive statistics found in like a previous study. So over here, you have your option for balanced sample sizes, and you can enter the mean for each group and the standard deviation for each group. Or if you have an unbalanced, or if you're taking results from an unbalanced study, you enter the means from each group and the pooled standard deviation. And yeah, so that's the pooled standard deviation. And so you can use that to do the calculation. And if you click the calculate button, it will just give you the number, but it won't change anything in the main window. If you click calculate and transfer, it does the calculation and copies the effect size into the main window for you. So the determine window for t-tests isn't all that interesting. So the example that I'll show you in a couple minutes, we'll actually use the numbers from the ANOVA example that Dr. Lomax gave earlier. And yeah, you know what? We'll just go straight to that right now. So now we'll do an a priori analysis for a one-way ANOVA. So to find the ANOVA tests, we need to change our test family to f-test. And then under statistical test, we need to go to ANOVA, fixed effects, omnibus, one-way. And this will do an a priori power analysis for a one-way ANOVA. And so the input parameters are basically the same as the t-test. You have your effect size measure, and for the one-way ANOVA, G-power is using effect size F. And so we'll do our effect size calculation in a second. You have your alpha level, you have your power, and so we'll change that to 0.8. And the last box is where you specify the number of groups in your design. And so the default value here is 5. We're going to change this to 3, and we're going to use the information from the sugar example where we have some evidence that there is an effect there, but we didn't have a large enough sample size to really detect it. So sticking with these initial values, when we click on determine, it opens up the effect size calculation panel, and the default selection is to calculate effect size from the means, and so you can specify the number of groups. Again, this is the within subject standard deviation, so that would be, I guess, a pooled standard deviation across the 3 groups. And you can enter the group mean for each of the groups and the sample size for each of the groups. So that's one option if that's the information that you have. The option that we're going to use is effect size from variance. So we change our procedure to effect size from variance. And here we have 2 options. Again, we can estimate effect size from variances. So this is the variance explained by the effect that you're studying, and this is the within group variance. The other option is to calculate effect size directly from partial eta squared. So if the study that you're referencing has provided partial eta squared, you can use that directly in your calculation, and it will convert that to Cohen's F. So we'll change this to 0.384, since that's the effect size that we observed on the example slide, and we click Calculate and Transfer. And so that translates to an effect size F of about 0.79. So we've transferred the effect size from that pilot study, and when we click Calculate, we can see that to achieve sufficient power, we would need a sample size of 21. So actually the sample size of 15, was too small, but we were pretty close. So we can, the effect size is large enough that we really only needed a few more people. So you can justify having a little bit of a larger study to follow this up. And you can see that the actual power here is 0.85, and that's just, it just takes the nearest calculation to get above 0.8. Yeah. And with all of these examples, if you click the XY plot for the range, you can create those same graphs that I showed you for the t-test. All of that stuff is the same for pretty much every type of statistical test. Okay. And how are we doing on time? Keep going? Okay. So now we'll look at an a priori analysis for a correlational study. So to find the correlation test that we want, we need to change our test family to exact. And we will do the default statistical test, which is correlations from a bivariate normal model. I'll close that for now. So in the input parameters, it's the same setup as the t-test. You have your one-tailed versus two-tailed test. You have the your estimated correlation under the alternative hypothesis. You have your alpha level, your desired power, and your correlation under the null hypothesis. So in most cases, when you're doing a hypothesis test about correlations, you're just testing it against a correlation of 0. So we'll just leave that at 0. And we change that to 0.8. And we'll just leave the correlation at estimated at 0.3 for the example. And we click Calculate. And so this is telling us that we would need a sample size of at least 84 subjects to achieve sufficient power if this is the correlation that we're hoping to detect. When you click on the Determine window, it will calculate this correlation based on R squared. And so it's just basically taking the square root. And yeah, so that one's not, correlation window is not all that interesting. So the next example I have ready is a multiple linear regression. And so for that one, we're going to go back to the f-test. And an important thing to actually make note of before we get to this is that under f-tests, we have linear multiple regression when you're trying to estimate or you're doing your power analysis for, I guess, testing how well the model fits. If you look under the t-tests, you have bivariate regression, so simple regression, and you have linear multiple regression. And those are listed under the t-tests if you want to do a power analysis to detect significant parameter estimates. So, For each predictor. So, for example, being able to detect a difference between intercepts or being able to detect a difference between slopes. Those are found under the t-test. We're going to go back to the f-test. And so we change that to f. We go to statistical tests, and we're going to select linear multiple regression for the fixed model with r² deviation from 0. Okay? And so under the input parameters, we have the effect size measure, f². We have our alpha level, our desired power, and we can just change that to 0.8, and the number of predictors in our model. And so the default value here is 2. For the sake of this example, we'll change that to 3. Okay? And so if you know what f² is, you can enter that here. If you don't know what f² is, if you click the determine window, you can estimate f² from a squared multiple correlation that was, perhaps reported with some previous study, or you can calculate f² from predictor correlation. So here you would enter your number of predictors, and you would actually have to specify your correlation matrix. So the first tab is where you would enter the correlations with your outcome variable. And then this window is where you would enter the correlations between the predictors in your model. So
You have to do both, or you just do one?
yeah, you have to do both. And you can enter those, and then you click calculate rho squared and click OK. I don't have an example correlation matrix prepared, but if that's what if that's the only information you have, that's how you would use the correlation matrix. We're going to go with the calculating effect size from the squared multiple correlation, and so we'll base this on maybe a previous study had an r² of 0.2, and so we click calculate and transfer, and that will do the calculation and copy it into the effect size window. We can close that and click calculate. And so given those input parameters, we would need at least a sample size of at least 48 subjects to have sufficient power for a multiple regression with 3 predictors. Okay. Let's see. Do I have time for 1 or 2 more? Okay. Great. So the next example I have is for a repeated measures ANOVA design, and we'll start with just testing for a between factors effect. And so we will go to, or I guess we'll stay under f-tests, and we'll change the statistical test to ANOVA, repeated measures, and between factors. Okay, so looking at the input parameters, we have our effect size, alpha, desired power, the number of groups in our study, the number of measurements, so the number of time points, and then this last window is where you can, or this last box is where you can specify the correlation among the repeated measures. And, okay. So the newest version, the newest Windows version that I've seen will have an options button there, and it will let you change how it's doing the estimation. So the default setting is, we'll ask you to report this correlation among the repeated measures. If you change the effect size specification to Cohen's specification, this will go away. But I think that by not specifying the correlation among repeated measures, it's a less powerful estimate of your required sample size. And if we click the determine window, we can estimate effect size from the means. And again, we're specifying the number of groups, the within group standard deviation, group means, and group sizes. Or if we do effect size from variance, we can enter the variance terms, or we can enter partial eta squared. And yeah, so you can enter it from previous research. You can, like I said before, you can estimate what you think the effect size is going to be and then try to plot that range of effect sizes. I would say you would probably want to be more conservative with your estimates of the effect size that you observe. But yeah, primarily we would take this from, we would kind of pull these results from previous studies or pilot studies. And so we click calculate, and this is saying that we would need a sample size of 82 to have sufficient power. And this is giving you the total sample size, so you would obviously probably, or you would probably try to split these, that sample size evenly between the two groups that you're studying. Okay. And, all right, so I have my, sure.
So assuming that you're going to divide that total sample size into equal groups,
Mhm.
what's the wiggle room around that? Right, to know if you don't get exact split,
Oh.
you know how far, if you get 82, how
Mhm.
far of a difference you get, you still have to.
I would say maybe a difference of, 4 or 5. I think you'd want to try to keep it pretty close if you can. If you are planning something that is a more like an unbalanced design, you would probably need to do some of those other calculations in a different program. But yeah, I would say that you have some wiggle room as far as how close the sample sizes are, but I would still, try to keep it as close as possible. Yeah. Okay. And so I have one more example here, and this is for repeated measures ANOVA, where you have a between subjects factor and a within subjects factor, and you're going to calculate power to detect an interaction effect. And so you can see that you have additional input parameters, and we'll talk about those in a second. We have the effect size, alpha, our power level, or desired power. We have the number of groups, number of time points. Again, if you have the newest update from G-Power, then you should have an options button here, so you can choose whether you are required to enter this parameter or not. And then the last input that it asks for is the non-sphericity correction, epsilon. And this is a correction, or this correction is used when you violate the sphericity assumption. And so the default value here is 1, which is assuming that you have perfect sphericity. So you're meeting that assumption completely. So that's often maybe a little bit unrealistic. So when you're doing these calculations, you would probably want to try running them with some smaller numbers. As the number gets closer to 0, that represents a larger and larger violation of the sphericity assumption. And so you can kind of play around with that and sort of simulate different scenarios where you're violating the assumption to different degrees. And so we'll leave those parameters set. If you click the determine button, you can estimate effect size from the variances or from partial eta squared. And so we have all of our information. We click calculate, and here you can see that to reach sufficient power, we need a sample size of 24. So I think this is a good example of where using a more powerful research design can improve your power and lower your minimum sample size that you require to detect a difference. Okay. And
You have 12 people in each group, is that right?
yeah. Yeah, 12 or roughly, try to keep it close. And yeah, so that's all I have prepared for the demonstration. If you want to, okay, cool. All right, thank you.
So we'll just finish up the slide so you can see what you're going to get. Basically, the bulk of the rest of the slides are screenshots using these same examples with some explanation since Robert won't be there. So I'll just kind of scoot through that. Here's the URL for getting G-Power. Again, it's free. It comes out of Germany, but it is in English. Here's a list of references of some, what we think are some key things that deal with power analysis. So we've got like Cohen's book is up there toward the top. Ellis is one where some of those interesting humorous bits came from. Again, there's some pieces on the abuse of post hoc power. Here's another book that I like by Murphy on power analysis, and then down toward the bottom is an article by Peng, which came out last year reviewing some of these power analysis programs. Also, the Ellis book that some of these things came out of, it can be obtained as an ebook for free through the OSU library if you wanted to have access to that. And so what we'll do is we'll take the slideshow and post it on the Office of Research website. I think what we'll try to do is compress this down and just send it around to each of you. Right now it's like about 12 meg, and so that's not going to go through the email system. And so I'll try to get that to you directly. Hopefully one of the things you gathered out of this is, number one, power analysis is easy to do. You can do it in 1 minute. All you need is an effect size from somewhere, or to use the calculator to compute an effect size, and so it's literally 1 minute of work. You can just cite that in your paper, in your proposal, what have you. Power analysis was done using G-Power. To achieve a power of 0.8, I need a sample size of 100. That's all you need. That will keep the reviewers happy. And so I guess sort of the bottom line is this is something that all of you can do very easily in 1 minute. Now, we're not saying G-Power is the one you should get, but it is the most comprehensive one for free. And so unless you have $700 sitting around, which I don't, then I might use something like this. Questions from anybody? Any additional questions? Okay, I want to thank Robert and Susie, who did almost all the work, for doing a great job. We do have one more workshop coming up in April. This is April 11th. It'll be in here. It's an insider's perspective to federal funding opportunities. And so we'll have 3 or 4 PIs from EHE talking about their experiences. We also have an NSF grant officer that will be coming here. And so again, that's coming up April 11th. Thanks for coming. See you guys.